Hi, my name is Matthew Smith. I'm a multivariable calculus student at the Belmont Hill School and proud 1 out of 6 scorer on the latest New England Math League competition. Today I'm going to talk about limits with my teacher. Sitting with me today is Mr. Feldman, my teacher in multivariable and BC calculus. Welcome, Mr. Feldman.
Thanks very much for having me. It's good to be here on Chalk Talk.
So let's get right into it. How would you define a limit?
A limit is a finite number to which the outputs of a function grow infinitely close.
Yeah. So as a teacher, what would you say are some of the things students struggle most with limits, and how have you helped them overcome that?
That's a great question. I think students struggle with different elements at different grade levels and content levels. I think the youngest guys struggle with the idea that we're not looking at the value of a function at a particular point, but rather as you are growing infinitely close, and this idea of infinitely close is a hang-up, for most folks when they first engage with limits. And I think a lot of it is about the language that you use and the visual aids that you produce, and the ways in which you get guys to sort of imagine themselves approaching something infinitely close without actually getting there. Or you remember from last year we talked about what happens not when x gets to 3, but when x gets really, really, really close to 3, or really, really freaking close to 3, or and then this idea of infinitely close without actually being there starts to set in, and then we mess them up a little bit later on when we say there's really no difference between infinitely close and being actually at the value, and that's another hang-up point. And then certainly as you get into more advanced number theoretical stuff, and looking at some more advanced functions, you get another level of hurdles when you're entering limits. It's one of those very dynamic topics that as soon as you think you got all there is to get, there's something else to introduce that sort of pushes your brain a little bit further.
Yeah, that's great. So over the past 2 years, one of the more advanced applications of limits we've talked about is the zeta function and the Riemann hypothesis. So could you talk a little bit more about that?
Sure, I can talk a little bit. And as you know, we've talked quite a bit about it. Bernhard Riemann was a German mathematician in the mid-19th century, and he did some really, really astounding work, published a paper in 1859 with his findings on this function that he defined called the zeta function. And the zeta function has inputs. At first, he looked at inputs which were just natural numbers, and then he started to expand the domain and look at what happens when you apply the Riemann zeta function to other inputs, the rationals, and then eventually all of the reals. And then he expanded it beyond the reals into the complex numbers, and that's where things start to get really interesting. It's one of those beautiful functions and beautiful branches of mathematics that was looked at for one particular reason, and then the further they looked at it, the more broadly they realized that this thing could apply to all kinds of different branches of mathematics. And actually, the Clay Institute of Mathematics has published a list of millennium problems in the year 2000, each associated with $1 million prize, and the Riemann hypothesis is one of those problems. And a lot of people say it's the hardest way to earn $1 million is by proving the Riemann hypothesis. And the limits as they apply to the Riemann zeta function, you're finding a sum of an infinite series, which is what we do a lot in BC calculus. And this particular series, when it takes on different input values, becomes really challenging to evaluate limits in order to actually calculate those sums. But those sums turn out to be really, really fascinating values, and have implications into, for a lot of folks, most interestingly, prime number theory and the distribution of the primes. And the actual Riemann zeta hypothesis is that the zeros, which is a topic that we study all the way from algebra 1 into advanced levels of mathematics, the input values of a function make the output 0, that the zeros of the Riemann zeta function lie on this vertical line in the complex plane where the real component is 1/2. And there are a handful of trivial solutions that live on the x-axis, but it's those non-trivial solutions that they're looking to prove. And so the hypothesis says that all of those solutions, those zeros, lie on the vertical line x equals 1/2 with different complex components, and thousands of zeros have been found on that line, but the hypothesis is yet to be proven or disproven. And so really all you have to do to win $1 million is to find some zero that doesn't live on that line, or the harder way is to prove that in fact all of the zeros, the non-trivial zeros, do live on that line. It's as rich within the applications.
Thank you for that, Ms. Froman. So I'm gonna leave you with one last question. It's a little difficult, but try your best to answer it. What do you see as the significance of limits?
Wow. Most personally, it's why I have a job. Calculus, the thing that is calculus is this idea of the application of a limit, and the fact that a limit has been verified and proven and is valid within the mathematical community allows us to calculate these things like area under a curve or instantaneous rate of change of a function, because we look at what happens when 2 points become infinitely close and we're still able to calculate a valid result. But you know, all of calculus is based off of limits, and therefore all of the applications of calculus and all the wonderful things that we've been able to do in the scientific and mathematical community as a result of having calculus as an asset or a tool. And there's all kinds of conjectures that have been proven in mathematics that do really powerful things that rely on the Riemann hypothesis being true. And so I think, you know, one of the next step in the broader mathematical community is to hopefully prove the Riemann hypothesis to be true, so then we can start using all of these things that we have built up in a warehouse somewhere, all these applications and really cool things that say, well, if the Riemann hypothesis is true, then we know for sure that these, you know, many different broad results are also true.
Yeah, that's really great. Thanks for being here, Mr. Froman.
Thanks for having me.
Hey guys, it's Austin from Chalkboard Math Tutorials. That was our series on limits. If you liked our last video, hit the like button below. Check out the other videos on our channel and subscribe. And the fourth row right here if you missed it.
Sitting with me today is Mr. Feldman, my teacher in multivariable calculus and BC calculus. Welcome, Mr. Feldman.
Well, thanks very much for having me. It's good to be here.
Yeah. So let's just get right into it. How would you define a limit?